Alright, so in this video, we're going to be practicing a bunch of limit problems, right? We're going to be looking at the main types of limit questions you may see in Calculus 1, AP Calc AB, BC, and we're going to go step by step on each of these problems, showing you substitution, factoring, the conjugates, trig limits, even some where the limit doesn't exist. So let's get right into it. And with each of these problems, I'm going to be putting them up on the screen, so feel free to pause and give them a go by yourself, and then you can follow along with the solution. But let's start off with this problem. What is the limit as x approaches 2 of 3x squared minus 5? So what is the limit as x approaches 2 of 3x squared minus 5? All right. So, how do we start? As with all limit problems, let's start directly with using substitution to see if we're able to, if that works. So in this case, we can see that using direct substitution, we are able to get an answer of 7. And so that's going to be the answer for this problem. All right. Let's look at the next one. What is the limit as x approaches 4 of x squared minus 16 divided by x minus 4? So with this problem, if we try to use direct substitution, we can see that we get 4 squared minus 16 divided by 4 minus 4. And this gives us that indeterminate form of 0 over 0. So we know that we can't use direct substitution. So let's try to factor this out. We can see that the numerator is an example of the difference of squares. So we can factor this out to give us the limit. So this is equal to the limit as x approaches 4 of x minus 4 times x plus 4 over x minus 4. This allows us to cancel out the x minus 4 from the numerator and denominator, giving us the limit as x approaches 4 of just x plus 4. So we were able to simplify this expression down to just x plus 4, where now we're able to use direct substitution, giving us 4 plus 4, and so our limit is going to be equal to 8. Okay, let's look at the next one. Let's say that we're trying to find the limit as x approaches 0 of the square root of x plus 4 minus 2 over x. So here, again, if we try direct substitution, we can see they will get square root of 0 plus 4 minus 2 over 0. 0 plus 4 is 4. Square root of 4 is 2. 2 minus 2 is 0. This gives us our indeterminate form as 0 over 0. So we can't use direct substitution. So whenever we see a limit where the function here has this sort of expression where we have a square root, this sort of binomial going on over here, well then we can use rationalizing. We can try to rationalize this function first. And what that means is we multiply by the conjugate. So in this case, we can then say that we get x plus 4 minus 2 over x, and we multiply by the conjugate of this numerator term. So that would just be square root of x plus 4 plus 2. So we multiply both the numerator and the denominator by this. Doing so, because of, again, the difference of squares, we are now able to get rid of this square root and simplify this expression. So if we think of this as our a term, and this as our b term, we can see that we're effectively doing a minus b times a plus b, which would give us a squared minus b squared. So, thinking of it like that, if we square this a term, the square of the square root of x plus 4 gives us just x plus 4, and the square of 2 is 4, so x plus 4 minus 4, and our denominator is then just going to be x times this expression of square root of x plus 4 plus 2. The numerator then can further simplify down to just x, and we get x times the square root of x plus 4 plus 2, and our x and x can cancel out. So if we make some room over here, we see that we end up with 1 over the square root of x plus 4 plus 2. Rather, this is going to be the limit as x approaches 0 of this. And if we then simplify this by substituting our value of x into this expression, we can see that we get 1 over the square root of 0 plus 4. That's the square root of 4, which is 2. 2 plus 2 is 4. So our answer then is going to be 1/4. So again, we just substituted our value here for our 0 into this expression. Hopefully this is making some sense. Again, if you have any questions, I have made a previous video where I went over, or where I go over, all of these different strategies that we can use to algebraically manipulate different limits in order to solve them. So let's look at the next problem. Okay, looking at this next problem, what is the limit as x approaches 0 of sine x over x? This is something that we should be familiar with, as this is one of our special trig limits that we should have committed to memory. So we know that the limit as x approaches 0 of sine of x over x, we know that that is just 1. So that is our limit. There's nothing we really solve here. This is just one of our limits that we commit to memory. Okay. Let's look at the next problem. What is the limit as x approaches 1, or rather x approaches negative 1, approaches negative 1 of x cubed plus 2x plus 1. So this is one of our polynomial functions. Is a continuous function, and so we should just be able to use direct substitution. So let's try that. Using direct substitution, we get negative 1 cubed plus 2 times negative 1 plus 1. And this gives us an answer of negative 1 minus 2 plus 1, or simply just negative 2. So this is our answer for this problem. So again, we always start by seeing if we're able to use direct substitution. That's always the easiest step. And if that doesn't work, then we can move on to more advanced or other techniques. But usually for these types of polynomial functions that tend to be continuous, if it is a continuous function, most of the time we can try to use just direct substitution. So let's look at the next problem. What is the limit as x approaches 2 of x cubed minus 8 divided by x minus 2? Okay, if we wanted to use direct substitution here, we would see that we would get 2 cubed minus 8 over 2 minus 2. 2 cubed is 8, and 2 minus 2, 8 minus 8 is 0, 2 minus 2 is 0. This gives us that indeterminate form, so we can't use direct substitution. Let's see if we're able to then, factor and cancel, right? So can we simplify this kind of higher power down? Well, what I like to do is oftentimes what you see with these types of problems where you suspect that you may be able to factor and cancel it out is if you look at the denominator, it kind of, a lot of the problems tend to give you a hint in that teachers or in your classes, whether it's the AP exam or your college classes, really what they kind of give you is if you see something like this where you see x minus 2 and you suspect that you're trying to factor and cancel, more likely than not the x minus 2 is part of the term when, or part of this numerator if you factor it. So what I mean by that is we can see that we can just say x minus 2 times some other expression, and our denominator is x minus 2. It's likely that they just want you to cancel this x minus 2 term from the denominator. So then we can see x minus 2 times what expression would give us x cubed minus 8. And, well, by factoring this out, we can see that if we get x squared plus 2x plus 4, if you kind of evaluate this out, it would simplify to x cubed minus 8. And so this would then allow us to cancel out x minus 2, leaving us with a much simpler expression that we can try to directly substitute our value of 2 into, which is just going to be limit as x approaches 2 of x squared plus 2x plus 4. If we substitute 2 into this, we get 4 plus 4 plus 4, which is just 12. And that is the answer for this limit. Okay, let's look at the next problem. All right, let's see. Let's try another trig limit. So what is the limit as x approaches 0 of tangent x over x? Well, tangent x is not one of our special trig limits that we've seen, but we know that tangent x is equal to sine x over cosine x. So let's try to use this in order to manipulate this, algebraically. So we can see that then we can rewrite this as sine x over x times 1 over cosine of x. Or rather, the limit as x approaches 0. The limit as x approaches 0 of this. And so then that allows us to effectively cancel this out, because we know that the limit as x approaches 0 of sine of x over x is equal to 1. So that leaves us with 1 times the limit as x approaches 0 of 1 over cosine x, which we can just use direct substitution to find, right? If we substitute 0 for our x over here, cosine of 0 is just 1. So 1 times 1 over 1 is equal to 1, and that is going to be the answer to this limit. Let us look at another example. Let's say we want to find the limit. Find the limit as x approaches 5 of 2x squared minus x. Well, this seems to be a continuous function that we can just use our direct substitution for. So we can do 2 times 5 squared minus 5, which is 2 times 25 minus 5, giving us an answer of 45 for this limit. Okay, now let's try to find the limit as x approaches 4 of the square root of x minus 2 over x minus 4. Now this is something, again, that we can try to use our rationalization, that technique, in order to solve this. And we see that because we have a square root, which we're going to want to get rid of. So in order to rationalize this, we're going to multiply the numerator and the denominator by the conjugate. So in this case, that is the square root of x plus 2 divided by the square root of x plus 2. Again, this is difference of squares, which allows us to simplify this to become the limit as x approaches 4 of x minus 4 divided by x minus 4. Okay, this is glitching a little bit. X minus 4 times the square root of x plus 2. This then allows us to cancel from the numerator and the denominator, leaving us with 1 over the square root of x plus 2, which we then, if we use our direct substitution, allows us to get 1 over the square root of 4 plus 2. Square root of 4 is just 2, so that gives us an answer of 1/4 for our limit. So hopefully you're starting to get the hang of these kinds of problems. You're able to recognize, just by looking at it, what approach you're going to want to take. Which is why we're just giving multiple examples where we use these different types of strategies, just so you get more of a feel of, just looking at the problem itself, you should kind of get an idea of the approach you want to take. And you can see that it does get somewhat repetitive as you start doing more problems, because, limits aren't, inherently super difficult. It's just there's a couple of types of problems that you can see, or a couple of strategies that you need to know, that if you mix together, you can basically solve any limit problem that is thrown your way. All right, now let's take a look at a problem that we haven't seen before, a type of problem we haven't seen before. What if we're trying to find the limit of a piecewise function? So let's take a look at this function first, and then we can see how we can find the limit. So let's say that our function f of x is going to be equal to x squared for all values of x less than 1. And it's going to be equal to 3x minus 2 for values of x that are greater than or equal to 1. And we want to find the limit as x approaches 1 of f of x. So how do we, approach this type of problem? What must be true in order for this type of limit to even exist? Well, firstly, if we want a two-sided limit, like the limit as x approaches 1 of f of x to exist, well, the left-handed limit and the right-handed limit both must exist and be equal. This is something that isn't different at all from what we've seen with any other limit, right? If we're looking at a graph, we see an approach from the left, and we see that it approach from the right, and if they converge at a single unified common point, then only can we say that the limit exists. If we have distinct values, the limit from the left approaches one number and the limit from the right approaches a different number, then the limit does not exist. So it's the same concept here. So if we wanted to write this symbolically, then we would say that the limit as x approaches 1 from the limit as x approaches 1 from the left must be equal to the limit as x approaches 1 from the right. And again, in both these values, they both must exist. Okay, so then let's first start by trying to figure out what the left-handed limit is. So what is the limit then? The limit is the limit as x approaches 1 from the left of f of x. Well, we need to first figure out which part of the function here, or which branch of this piecewise function we're actually going to use for this part of the problem to find the left-handed limit. And this can make some sense, or we can figure this out by if we want to look at, a number line. If we have a number line where we have, 1, 0, 2, we can see if we're approaching this value of 1 from the left, if we're approaching it from the left, all of these values before we reach 1, all of these values are going to be less than 1. And so, if that's the case, well then we're going to have to use this branch of the function, right? Because this branch, f of x is going to be x squared for all values of x less than 1. That means, that covers this exact instance. So as opposed to just leaving this as f of x, we can say the limit as x approaches 1 from the left of x squared. And we know that x squared is a polynomial. It's continuous everywhere, and so we can just use direct substitution to see that 1 squared is equal to just 1, and so the left-handed limit is 1. So the limit from the left-hand side, if we want to write it like this, is going to be equal to 1. So now let's find the right-hand limit. So what is the limit? What is the limit as x approaches 1 from the right? Well, again, we only have one branch left, but just thinking about it conceptually again, if we had our number line, if we're approaching the value of 1 from the right now, we're coming from the right, well then all of these values that we approach, or all these values that we pass before reaching 1, they are all going to be greater than 1. And if that is the case, well then we will be using this branch of the function, because f of x is going to be 3x minus 2 for all values of x that are greater than or equal to 1. So again, that is this, that's this case here. So we can change our f of x here to 3x minus 2. Again, 3x minus 2, that is a polynomial, it's a continuous function, so we can directly substitute our value here, giving us 3 minus 2, or 1. And so we can say that our limit from the right-hand side is also equal to 1. And so here, since the limit as x approaches 1 from the left, the limit as approaches, again, of f of x is equal to 1, which is equal to the limit as x approaches 1 from the right, we can say that this limit, this two-sided limit, does indeed exist. And as a matter of fact, this limit, again, as x approaches 1, of our f of x, this piecewise function, is going to be equal to 1. So that is how we approach this type of problem. You're often going to you're going to have to include this type of work to show that the left-handed limit and the right-handed limit do equal the same value. So that's kind of a piece of work that is necessary. You may be required to show in order to get full credit. But this is the way that we approach finding the limit of a piecewise function. But that brings us to the end of this video. We looked at a couple, of different limit problems here. Hopefully this was, good practice. You got some utility out of this video. If you did, please show your support by liking and subscribing, and, leave in the comments what you'd like to see next and any questions that you may have. But we'll see. I'll see you in the next video.